Some people seem like you're a little bumpy on the algebra of using logarithms to undo exponentials. So here's 3 problems where you might be asked to solve for x. And what's common to all of them is you've got a base to some power, and x is in that power. So in all 3 of these cases, we're going to have to use logs to get the x's out of the exponent. We need to cancel the exponents. Your eyes may be more used to thinking about this kind of situation where you have roots. Like, you don't need to think very hard to know that to undo a cube root, all you've got to do is cube it. So in this situation, here I've got a square root. So to undo it, I'd square both sides. And so I'd have root x minus 7 equals 9 squared. And then I could add 7 to both sides and then square it again, and I'd be done. In this case, it's an 11th root, so I'd need to raise both sides to the 11th power. So I'd have 4 to the 11th equals 11th root to the 11th power, and those would undo each other. And so then I have this, and now I've got a normal equation that I could just solve. In this one, you wouldn't want to raise both sides to the 7th power yet, because if I raised this side to the 7th power, it would be 2 terms, and I'd have to multiply it all out. So you need to isolate the term that you're trying to undo. So in this case, what I could do is let's add the entire 7th root to the right-hand side and subtract 12. So here I'd have, what's negative 7 equals 7th root 2x plus 1. And then I raise both sides to the 7th power. And here, raising this to the 7th power undoes the 7th root. And now you can be solving. So that's the kind of idea. The idea is isolate the root and then raise to the power that you need in order to undo it. So the same strategy applies here. Here you want to isolate the exponential term and then use a logarithm of the right base to undo it. So for this equation, we already have an exponential that's isolated. So if I want to undo 2 to the something power, I will take log base 2 of both sides. What is log base 2 of 9? I don't know. It's the power of 2 that will give you 9. So I know it's larger than 3 and less than 4. And you could, like, evaluate it with a calculator if you want to. But my point is you've got some number on the right-hand side. Here, the log cancels with the exponentiation, and you've got root x minus 7. And now you've got a problem that you can solve. You isolate the root and undo the root. Same thing here. Here I've got 11 to the power of something, so I need to use an 11th root. So I'd say, sorry, a base 11 logarithm. So I'd have log base 11 of 4 on the right-hand side. I'd have log base 11 of 11 to all that stuff in the exponent on this side. These undo each other, and so I'm left on the right-hand side with just x squared plus 2x plus 1, and on the left-hand side, this is just some number. And again, you know how to solve that one. Here, you'd want to isolate the term with the exponent first before undoing it. So just like last time, let's add this to the right-hand side. Let's subtract 12. So here I've got negative 7 equals 7 to the 2x plus 1. Here I'll take log base 7 of both sides. On the right-hand side, these undo each other, so I've just got 2x plus 1. On the left-hand side, if you try and evaluate this with a calculator, it's going to give you an error. And I hope that it's clear why if you think about the meaning. We're asking what power of 7 will give me negative 7. And there is no exponent where I could have 7 to that power and get negative 7. So there is no solution to this expression. There is no number that satisfies this description. So that's an indication that there is no solution to the original problem. So that's just another lesson in don't mindlessly apply algebra. Like at each step, you want to be thinking about the meaning of the terms involved so that you can catch things like that. Okay, I hope that this was helpful.